Hey everyone, welcome to the second video in our series on the reactions of chapter 11. So in the last video, we talked about oxidation of alcohols. In this video, we're going to be talking about conversion of alcohols into alkyl halides. Okay, so there's three ways we can do this, and I will talk about all three of them here, but this is conversion of alcohols to alkyl halides. Okay, so like I said, three ways we can do this. One way is we can do this with HX. Okay, so if we do this with HX, then H can be, or excuse me, X can be Cl, Br, or I, right, as usual, and rearrangements are possible. So rearrangements can happen with this, okay? I can use any degree of alcohol as well. So like, let's say I use a 1 degree alcohol for this reaction. So what I do is I put in HX. So in this case, I'm going to use HBr, and then I'm going to use water. So HBr with water, what that's going to give me is the OH is going to get replaced by a bromine. That's it. Okay. So these are very simple reactions. There's not a lot going on here, but still important to know nonetheless, right? Additionally, if I use a 2nd degree alcohol like this, if we take a look at this one, you'll see that if I form a carbocation here, I can have a hydride shift to this, which will occur. So if I use HI with water, then I'm going to get the I here because of that hydride shift. Okay. And I can also do this with 3 degree alcohols as well. So let's do a 3 degree alcohol, tert-butanol. I'll use HCl with water. The important thing to note about HCl is that it only works with 3 degree only. Okay, so 3 degree alcohols only work with HCl. If I use a 2 degree or 1 degree, it's not going to work. And that's just because HCl is not a great or Cl minus, excuse me, is not a great nucleophile. So I have to use these 3 degree alcohols in order to actually get HCl to work properly. All right. Okay, so now that we've discussed this, there's two things mechanistically here that I kind of want to mention. Okay, so the first thing is that whenever I have a primary like this, it's going to go through an SN2 type mechanism. So I'm going to do the mechanism for this one first. So I'm going to do the mechanism for this one with the HBr first. Okay, so what happens is we have water in solution, right? So we have water in solution with the HBr. And we know that the water can get protonated by HBr, so that's what's going to happen. So water is going to get protonated by HBr, and then we get H3O plus and Br minus. Br minus is going to be important later. Okay, so now we have H3O plus and Br minus. So now our alcohol can come in. We can use our alcohol now. And just like a lot of other mechanisms that we've seen, this alcohol is going to get protonated by H3O plus. And then I get this, right? I also get water. So now, after I protonate this, what can happen is this bromine that I made earlier, negatively charged bromine, is a good nucleophile, and it can come in and it can do SN2 and it can attack that, and that'll leave. So what does that give me? Well, it gives me my product, and it also makes water. Okay. So this is the mechanism for what it looks like with 1 degree. So this is 1 degree mechanism. So the mechanism for 2 degree or 3 degree is slightly different. Okay, so I'll do the mechanism for this one with HI since there's a shift in it. Okay, so for this, it kind of went through an SN2 mechanism. For 2 degree and 3 degree, it goes through an SN1 type mechanism. Okay, so it goes through an SN1 type mechanism. So what that looks like is I protonate again, so water. And this time I have HI. Water's going to take the hydrogen off. Then I get H3O plus, and I also get I minus. Okay, so now that I made H3O plus, we're going to do a very similar reaction to what we did last time, right? So now H3O plus is going to protonate this. So H3O plus comes in, protonates. And now it follows an SN2 type mechanism. So what that looks like is, or excuse me, SN1. I said SN2, sorry. So now leaving group leaves. After being protonated, then I form a carbocation, right? Whoop. Also got water there, right? So now this is why this shift occurs. This hydrogen, we can have a hydride shift to this carbocation, right? So now if we have that hydride shift, then I form my carbocation there. And then as the very final step, I minus is going to come in and it's going to attack the carbocation. And then I'm done. So this is my mechanism for a 2 degree or a 3 degree. A 3 degree would follow the same type of mechanism, right? So this one with HCl, I would protonate the OH, and then the OH2 would leave, and then I'd get a carbocation, and then the Cl would attack the carbocation, the 3 degree carbocation, and then that would give me my final product. Okay, so very similar reactions there. Okay, so this is one way that we can do this, right? And there are other ways that we can do this. So let's take a look at a couple other ways. So we could use this with 1 degree, 2 degree, or 3 degree, with the caveat being that HCl only works with 3 degree. The other two ways, we only really use them with 1 degree or 2 degree, okay? We only really use them with 1 degree or 2 degree. So in these two ways are something called PBr3, which there's also PCl3, and we can make PI3 in solution as well, but we're not going to worry about that. So PBr3 is one. Works with 1 degree or 2 degree, and no rearrangements. Typically, no rearrangements. We're not going to worry about rearrangements, but know that it can happen, but we're not concerned about it. And then the other way that we can do this is SOCl2. That's a C. And this also works with 1 degree or 2 degree, and no rearrangements. And this also causes inversion of stereochemistry. I cannot spell today, I'm sorry. Okay. So we'll do these side by side. Okay. So very simple. Basically, what I do is if I take PBr3 with some 1 degree or 2 degree alcohol, so I'll do 2 examples. So we just put it in with PBr3. And PBr3, I can actually do this 3 times, but just show it once here. And again, all it does is it just replaces the OH with a bromine, right? That's the whole reaction, right? Not very complicated. Also, if I use a 2nd degree alcohol with PBr3, then I get a 2nd degree alkyl halide, right? And that's it. Mechanistically, we can talk about it, but I'm not too concerned about it. I don't think it's not a huge deal, so we're not going to worry about it too much. Okay, so this is one way that we could do it. No rearrangement, right? And 1 degree or 2 degree. Additionally, we can also do SOCl2. So SOCl2, thionyl chloride. Typically, I do SOCl2, and with it, I usually use pyridine. Okay, because this produces HCl, and so we want to use pyridine to get rid of the HCl. Okay, so now I just write HCl. I just write Cl instead of OH, right? And same thing here. If I use 2nd degree, works just as well. SOCl2, pyridine. Then we get the Cl. The only other thing to mention is that this does occur with inversion of stereochemistry. So if I start with this on a wedge, then my product is going to be on a dash, and vice versa as well, right? So if I start with some molecule that has OH on a dash, and I use SOCl2 with pyridine, then I will get the Cl on a wedge. Okay. So that's really all to mention about these two. Okay. So no rearrangements for both. One of them has inversion of stereochemistry, and they both work with 1 degree or 2 degree alcohols. That's it. Okay. So mechanistically, I'm not going to worry about these two, but there are mechanisms for them, obviously, as there is for everything, but we just won't worry about them. So that's all for this video. In the next video, we're going to very, very, very quickly talk about sulfonate esters and what they can do. And then I think we're going to talk about Williamson ether synthesis after that, and then we're going to be done. So hopefully this video was helpful. I appreciate you watching, and I will see you in the next one.